Okay, cool.
So the whole takeaway is if you want to say anything about this series, you just need to say something about the limit of this sequence. And we have some theory to study sequences. Let's try to use the theory for sequences and hit series with that. Here's maybe a super easy example. Let's suppose I give you two sequences, a sub k and b sub k. I tell you the sum of the series a sub k, where k runs from 1 to infinity, converges to a, and the series from k equals 1 to infinity of b sub k converges to b. Then where do you think the series of a sub k plus b sub k, where k runs from 1 to infinity, should converge? A plus b, right?
And maybe like the motivation should be like, well, I could move all the a sub k so they come first. I can move all the b sub k so they come last. If you want to go on to like all the way to infinity, that doesn't quite work, because then you'll never finish listing all the a sub k's before you can get to the b sub k's. But that's okay. We don't want to compute any infinite sums. We want to compute sequences of finite sums. So that's how we'll prove it. Let's prove it. So I'm going to only prove, oh well, what if I multiply all the terms in a sequence by a constant c? What should that do to the sum?
Pull that out of the sum, so it should just be c.
Yeah, it should converge to like c times wherever the sum of the a sub k is converged to. So you should be able to, like, even for an infinite series, factor a constant. I think this one might be a homework problem. So let's let a sub k and b sub k be sequences. Let's let a and b be numbers. And let's suppose that the sum of a sub k is converges to a, the sum of b sub k is converges to b. Well, that means something in terms of sequences of partial sums. Right, that's the definition. So let's let Sn and Tn be the sequences of partial sums for these series. What's the definition of the sequence of partial sums for the sum from k equals 1 to infinity of ak?
A1 plus A2 plus A3.
On up until, how many terms should I list? It's S sub n. I should list n of them. So I'll use summation notation for that because I don't have enough space to write all n terms. And Tn, I will similarly let be the sequence of partial sums for the sum of bk's. Nice. All right. So by assumption, then, what can you tell me about the limit of Sn? Converges to a. What can you tell me about the limit of Tn? Converges to b. Okay, so we've like unpackaged all of the hypotheses there. And we want to prove something about the infinite series of things that look like ak plus bk. So how do you understand an infinite series? You have to think about the sequence of partial sums. Let's let Rn be that sequence of partial sums. So Rn is a sum from k equals 1 to n of ak plus bk. That is the sequence of partial sums for the sum from k equals 1 to infinity of ak plus bk. And let's figure out what it is that we want to show. We want to show that Rn converges, right? Where do we want to show that it converges?
A plus B.
Okay, nice. And let's see, addition is commutative, right? That's one of the field axioms. So if I add finitely many numbers, I can rearrange the order in which I add them up. So instead of adding these up as a1 plus b1 plus a2 plus b2, how could I reorder those so I see Sn and Tn showing up?
Just arrange it to be the summation of A plus the summation of B.
Yeah. And obviously these parentheses don't matter, but I think maybe they're good for emphasis. And now we have exactly the sum of the AKs, k equals 1 up to n, plus the sum of the BKs, where k equals 1 up to n. equals Sn plus Tn.
Everyone feel pretty okay? And like, now it's obvious, right? Where does Sn converge? Where does Tn converge? Where does Sn plus Tn converge? By a limit law.
So, by assumption, Sn converges to A, Tn converges to B. We just said that Rn is equal on the nose to Sn plus Tn. So it has to converge to A plus B by limit laws.
So the sequence of partial sums for AK plus BK converges to A plus B. So where does the series converge?
A plus B. And that seems sufficient.
Cool. What do you think of that? That went okay? So what the takeaway there is, if I ask you to prove something about series, chances are you'll want to use something you know about sequences. And there aren't actually that many examples of series that in this class we will be able to compute on the nose. In general, it will be too hard to compute the value of series on the nose. Generally, we'll settle for short that they converge. And then if you want to know what the series is like close to, well then plug in n equals a billion and see what happens. You have a computer, you can perform a sum of many things. Just not infinitely many. A computer won't be able to do infinitely many computations.
There are, if you like, only two series I'll be able to compute on the nose. Two types of series. One of them will be geometric series. So here's a general formula for the geometric series. The sum from k equals 0 up to infinity of p to the power k is equal to 1 over 1 minus p. How many people are upset that that series begins its index at k equals 0? Okay, good. There's nothing special about sequences starting at k equals 1. Sequences can start at k equals 0. The sum from k equals 0 to infinity of pk is equal on the nose to 1 over 1 minus p if the absolute value of p is less than 1. Otherwise, that infinite series diverges.
And if you like, the reason that we'll be able to prove this is because geometric sums evaluate very nicely. For any number p other than 1, the sum of the first k powers of p is 1 minus p to the n plus 1 divided by 1 minus p. How many people went and looked up a proof of that claim? Okay, well, I'm going to continue to not prove that claim. I'll continue to say, if you want to prove it, well, there's one strategy, expand that. Another strategy is induction.
So let's, I'm going to use this claim but not prove the claim. So now I'll prove the proposition. Consider any p inner, and let's assume that the absolute value of p is bigger than 1, so if you like, I'm going to try to prove the false claim. So I want to prove that the sum from k equals 0 to infinity of p to the k is equal to 1 over 1 minus p. Well,
let's think about the sequence of partial sums of the series. Let's let Tn be the sum from k equals 0 up to 1 of p to the k. But what is that equal to by the claim that we're not going to prove?
well, that's what we're trying to prove about the infinite series. 1 minus p to the n plus 1 over 1 minus p? Or is that exactly what you said?
So, well, great. That means I have an exact value for what Tn is equal to. It's equal to that. So I just need to compute the limit of this blue expression. Let's just think about that. The only place I see any n's is p to the power of n plus 1. If the absolute value of p is less than 1, then what can you tell me about the limit of p to the n plus 1? It converges to 0.
Since absolute p is less than 1, limit of p to the n plus 1 is equal to 0. So limit of Tn, well, that's the same thing as limit of 1 minus p to the n plus 1 over 1 minus p.
Well, limit laws, right?
You can move the limit to the limit of the numerator divided by the limit of the denominator as long as you don't divide by 0. You don't. And now limits distribute over addition and subtraction. So the sequence of partial sums for the series converges to 1 over 1 minus p, which is exactly what it means for the series to converge to 1 over 1 minus p. How do you guys feel about that? That seem okay? I'm not going to prove the divergence result. Do you think that most of the proof of the divergence result will be like the exact same, except you'll say that the limit does not exist? I guess the only one that would be different is the case that p is equal to 1, because you won't be able to use this formula. This formula is not true when p is equal to 1 because the right-hand side does not exist. But what is the sum of 1 to the 0 plus 1 to the 1 plus a bunch of 1s up to n? What's 1 plus 1 plus 1 plus 1 plus 1? 5? So I think it just grows like n. I think that s of n will be like n plus 1 because it starts at 0. But tell me, what's the limit of n plus 1 as n goes to infinity? Infinity. In particular, it diverges. There you go. You guys feel pretty okay with that?
Quick question. I guess I just didn't understand, like in the first line of the proof, aren't you basically kind of like assuming your conclusion? Because you're saying, suppose you have absolute value p less than 1, then by claim 2.8.4, which is what you're trying to prove.
No, I'm trying to prove the proposition.
Oh, got it.
Yeah, I'm not going to prove the claim. The proof of the claim is not analysis. The proof of the claim is algebra.
Got it, thank you.
Yeah. Yeah, so I won't prove this. Unless you want to like come by my office and like see a proof presented during office hour. But I think the proof is easy enough that you all can figure it out / read it. So there's the first type of series that I'll be able to prove convergence. Here's the next type of series I'll be able to prove convergence. The telescoping series. So let's let Cn be any sequence, and let's assume that Cn converges to some number C. Let's let AK be given by the difference between two consecutive C's. Then the sum from k equals 1 to infinity of AK is equal to C1 minus C. And let's try to prove that. Let's let Cn be a sequence which converges to some number C. Let's let AK be a sequence given by AK equal to CK minus CK plus 1. Right, a sequence where the independent variable is K can't be the same as a sequence where the independent variable is N. Okay, cool. And some of this will be on the next page, but maybe I'll like some of the stuff here anyway. I want to prove something about the infinite series. What is the infinite series defined in terms of?
Okay.
Well, this is maybe too ambiguous to think. It's the sequence of partial sums. So let's let Tn be the sum from k equals 1 to n of AK, be the sequence of partial sums. So basically, I just need to show that Tn converges to C1 minus C. Well, let's actually just write down what Tn is and expand it. Expanding. See, Tn, that'll be like A1 plus A2 plus A3, all the way on up to An. And now let's expand out what each of these AIs are. Right? AK is CK plus 1 minus CK minus CK plus 1. So this will be C1 minus C2 plus C2 minus C3 plus C3 minus C4 plus dot 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 plus a C n minus Cn plus 1.
Do you notice anything that's going to like cancel in that expression? Everything except for like the very first term and the very last thing?
And it'll keep on going. The Cn will cancel with the term immediately before that's not being listed. Cool. So, well, I used the wrong letter. It's called Sn here. So eventually we got down to Tn is equal to C1 minus C to the n plus 1. So that means the limit of Sn should be the same as the limit as n goes to infinity of C1 minus C to the n plus 1.
What's the limit as n goes to infinity of C1? C1, it's constant. What's the limit as n goes to infinity of C to the n plus 1? Rather, C sub n plus 1? Yeah, by assumption the Cn's converge to capital C. Is Cn plus 1 a subsequence of Cn? So what does it have to converge?
Capital C. So maybe I'll indicate that these are actually lowercase c's by turning them into cursive c's, which maybe just look like tidal waves.
Cool. Have we just shown that the sequence of partial sums converges to a number? And that's all it means for the series to converge to that number.
Thus, the sum from k equals 1 to infinity of ak, that's the same as the limit of the sequence Sn, is C1 minus big C.
How do people feel about these ideas? This all seems pretty okay? Let's do an application. So let's let ak be 1 over k times k plus 1. And you'll notice I'm starting right here, that's the same thing as 1 over k minus 1 over k plus 1. Is that actually true? Is that actually a true equality? And it's even like an obvious one, right? You guys are just looking at it with a very neutral expression. Okay. Then I claim that that series converges. In fact,
Let's do better than that. Let's say where it converges.
so this is supposed to be a corollary, so presumably we'll just use the alternating series formula on the previous page. So let's let ak be 1 over k times k plus 1, which is the same as 1 over k minus 1 over k plus 1. Well, I want to realize that as like a difference between two consecutive terms in some sequence. Is that obviously equal to the difference between two consecutive terms in some sequence? What sequence are you thinking of? What should Cn be?
Over n or something.
Yeah, well, it's sub n, so let's make it 1 over n. Then, Cn converges to something. What's the limit as n goes to infinity of 1 over n? And Cn plus 1 minus Cn.
Actually, let's make this k. Ck plus 1 minus Ck. Well, that's the same thing as... Oh, no, Chris, no. Ck minus Ck plus 1. Let's expand out what that is.
What's Ck the same as? 1 over k.
Minus 1 over k plus 1. Is that the same thing as ak?
Yeah.
Sure is. Have we just realized AK as a difference between two consecutive terms in some sequence whose terms converge? Yeah, right? So as an immediate corollary of this previous proposition, proposition 2.8.5, hopefully that's correct. Yeah, the telescoping series. We conclude that the sum from k equals 1 to infinity of AK is equal to C1, but what is C1? 1. Minus, what's the limit of this, of the C's? 0, which is just 1. So this series converges to 1. How do you guys feel? That seem okay? Nice. So there's a break here in the notes for some homework problems. Maybe I'll describe what is in this set of homework problems, and then I'll keep going through the notes, and we'll just see how far I go. So the first thing that I'm going to have you guys prove in the homework is if you have a series that converges and you multiply all the terms by a constant, you can pull that constant out, which maybe you guys even see why that should be true, right? Because it should be true for the sequence of partial sums on the nose, and then you just put a limit in front of things and nothing breaks. Let's suppose that AK is 1 over root k minus 1 over root k plus 1. Does that look like something to which the telescoping series test might apply? Yeah. The last and maybe most interesting thing I'm going to have you guys think about is the idea of absolute convergence. So a series converges absolutely if it converges even after you put absolute values around everything inside. So far, all of the series we've actually seen explicitly today were absolutely convergent because there were no negative signs anyway. So I'll call a series that converges, which has the property that it converges even when you put absolute value pairs around the individual terms, absolutely convergent. Is there anything in that definition that says that an absolutely convergent thing must be convergent? It would be really silly, though, if something could absolutely converge and yet diverge. Anyway, let A be a sequence of numbers. If the sum of AK converges absolutely, then, oh, Chris. No absolute values if the pair is there, otherwise it's just the definition. If a series converges absolutely, then that same series converges. So just take the absolute value pairs out of the conclusion. And there's even like a guided proof on the next page that'll help you think about it. If you like, it results to the word Cauchy. So those are the things that I want you to do in homework, but I think, given the fact that I haven't used up much time, that we should keep on going. So far this probably all felt super familiar because of calculus 2, right? In Calc 2, you got pretty good at thinking about a series of numbers. In particular, you got lots of tests for convergence in Calc 2. One of them was the geometric series test, or maybe most Calc books call it like the P-series test or something. What are some other tests for convergence that you remember?
Remember how to do or remember of?
Remember of. Just any buzzwords you remember that's like a test for convergence.
Ratio test?
Ratio test, good.
Integral test? What was one?
Integral test, good. We won't hit the integral test because we won't hit integration in this class.
You can compare it with like comparison test.
Comparison tests. That's a good list. Maybe the only, so another one that we won't explicitly use in this class is the alternating series test, which says that it's really easy to get a series to converge as long as you keep alternating between plus and minus signs. If you like, that will be basically one of the options for final project. And which includes some other things about non-absolutely convergent series. Let's start proving some of these comparison tests. In particular, let's prove some of these tests for convergence in particular. Let's start with the comparison test. And if you like, so you said the ratio test, right?
Mm-hmm.
How do people also remember the root test? Not necessarily the statement, but the phrase the root test. Both of those, the ratio test and the root test, the proof will just amount to a comparison test with a geometric series. So what I want to hit in this note pack, which maybe I'll make it through, maybe I won't, will be walking towards the proof of the comparison test. And it's going to pass through the idea of absolute convergence. So, that's a double error. No absolute value bars there. So what you'll prove in homework is, yeah, a series converges even after you put absolute value bars around it, then it converges without those absolute value bars. And I'll call the first type of series absolutely convergent. But let's think about this series where you only add up positive terms. Well, if you only add up positive terms, when you add more of them, the quantity that you're adding up only gets bigger. What do you call a sequence that only gets bigger as n increases?
Monotone increasing.
Monotone increasing. And we have some good tests for convergence of monotone sequences. Let AK be a sequence of numbers. Then the sequence of partial sums, Sn equal to the sum from k equals 1 to infinity of the absolute value of AK is a strictly increasing, well, is an increasing sequence. The AKs might all be 0 though. Let's prove that. And the proof seems like pretty obvious, right? When I add more positive numbers, I can only make the total bigger. So the proof should be super easy. So let's let Sn be the sum from k equals 1 to n of AK be the sequence of partial sums for the sum from k equals 1 to infinity of the absolute value of AK. Let's consider any n in the natural numbers. If I want to show the sequence is increasing, then S sub n plus 1 had better be than S sub n. Greater than or equal to. Well, let's prove exactly that, and let's prove it by analyzing what Sn plus 1 is equal to. So Sn plus 1, by its very definition, should be the sum from k equals 1 to n plus 1 of the absolute value of ak. And maybe I'll even expand it out. Maybe you don't want to. a1 plus absolute a2 plus plus absolute an plus absolute an plus 1. So that's just expanding out what the definition of the n plus 1 partial sum is. Or n plus plus, depending on which you prefer. Do you see like Sn somewhere inside of that? Yeah. So that's the same thing as Sn plus what? A sub n plus 1. Oh yeah. That's important. So there's Sn right here, in this pink subsum, plus absolute a sub n plus 1. Since Sn is exactly absolute a1 plus plus absolute a n. So tell me, this quantity, absolute value of a n plus 1, is there any danger of it being like negative? It's an absolute value of something. It can't possibly be negative. So a sub n plus 1, absolute a sub n plus 1, is definitely bigger than or equal to 0. And so it must be that Sn plus 1 is bigger than or equal to Sn. So the sequence Sn is increasing. I don't like the one by assumption there because it's not an assumption anymore, it's a conclusion. It's because it has an absolute value bar around it. Nice. So let's notice something. When does a monotone sequence converge? What extra hypothesis do I need to conclude that a monotone sequence converges?
It's bounded.
It's bounded.
And if it's an increasing sequence, I just need it to be bounded above. It's automatically bounded below by like S1. So there should be an easy test to see if that infinite series converges. It should converge if and only if, well, this sequence of partial sums for the infinite series is bounded above. But it should be super easy to check for boundedness. That's like such a light property. You just need to find an upper bound. It doesn't need to be the best upper bound. You just need to find one. So here's the most obvious application. So let's let AK and BK be sequences of numbers. I'm going to fix some starting index big N. So all that means is I'm fixing some natural number big N. The word index doesn't really mean anything. It just is supposed to tell you that that's just supposed to control what indices, what subscripts I'll care about. Let's suppose that absolute value of AK is less than or equal to BK for all little k bigger than big N. Sorry, this has more typos than I would prefer. If the sum of BKs converges, then so does the sum of absolute AKs. If the sum of absolute AKs diverges, then so does the sum of BKs. Cool, so let's just check out this false bit. So that means if I can find a sequence BK which is always at least as big as AK, but maybe is much easier to study directly, then as long as BK exceeds AK eventually, I should be able to conclude that if the sum of BK converges, maybe I can get BK to be like a geometric series, then so does the sum of absolute AKs. How does that seem? That seem okay? So let's try to prove it. And maybe I've sold a bunch already. What sort of strategy do you think I'm going to try to use to conclude that the sum of absolute AKs will converge? Well, so far I've shown that the sequence of partial sums for the AKs is monotone increasing. So what do you think I still need to show about the sequence of partial sums for the absolute value of AK? Bounded. That's all I need. That's all I'm going to try to show. I'm going to try to show that the sequence of partial sums for the absolute AKs is bounded above. So, in fact, look at the difference between statement 1 and statement 2. Like, if statement 1 is P implies Q, then statement 2 is not Q implies not P. Those are like the exact same statement, right? So I'm not even going to be like, I'm only going to prove one and leave the proof of the other to you. I'm going to say I'm only going to prove one. The next is logically the same statement. So I'm only going to prove claim 1. Let's let AK and BK be sequences of numbers. Let's suppose there exists some big N such as the absolute value of AK is less than or equal to BK for all k bigger than big N. And let's also suppose that the sum from k equals 1 to infinity of BK converges. So let's let Sn be the sequence of partial sums for the absolute value of AK, for the sum of absolute value of AK. So Sn is the sum from k equals 1 up to n of absolute AK. And let's let Tn be the sequence of partial sums for the BKs. So let's just try to parse out the assumptions first. What do I get to assume if I want to prove that if the series BK converges, then the series of absolute AKs converges? Sorry, that was too long a sentence. I know something about either Sn or Tn. I know something about Tn. What do I know about Tn?
It converges.
Converges. So I guess that's probably on the next page. Since the series of BKs converges, the sequence of Tn's converges. example, I want to do something about boundedness of the end result series. So tell me, do convergent sequences have to be bounded? Can an unbounded sequence converge? No. And in fact, that's something that we proved, right? So that sequence Tn, is it bounded? That's encouraging. So let's do that. So let's Tn, I'll rewrite that as a sum from k equals 1 to n of bk. That's not rewriting it, that's exactly its definition. I'm going to re-express that, however, by first adding up the first n minus 1 terms, and then adding up the remaining terms. And I can do that as long as little k is bigger than or equal to 1, right? I can list the first couple terms and then I can list the rest. So, since the sum from k equals 1 to n of bk, no, I think this is what I want. The sum from k equals 1 to n of bk. Let's solve for that. So if I take this expression and I solve it for just that last term, I could do that, right, by just subtracting off the first sum. So the sum from k equals big N to n is the same as t sub n minus the sum from k equals 1 to big N of bk. Let's see. Is this sequence convergent? Is the sequence convergent in the variable little n? Are there any little n's in it? So what type of sequence is this one? It's constant. Do constant sequences converge? Yeah. So since these sequences are, so since Tn is convergent and the other ingredient, the sum from k equals 1 to big N of bk is constant, it follows then that the sum from k equals big N up to little n of bk is also convergent, and in particular it's bounded. And so is bounded. Let's let u be an upper bound on the sum from k equals big N up to little n of bk. How do we feel about that? Are we happy so far? Yeah.
Should the constant summation be going to n or n minus 1?
Yeah, you're right. It's all wrong. It should be running from k equals 1. Oh, that one. Yeah, there we go. Big N up to little n. Yeah. Okay, good. Well, I think I might have an off by 1 error in my indices anyway. Let's see if you guys notice it. So let's not consider any little n bigger than big N. Then Sn is exactly the sum of all of the absolute AKs by the definition of Sn. So I can similarly break that up as the sum from k equals 1 to n minus 1 plus the sum from k equals big N up to little n is less than or equal to this constant number plus the sum from k equals big N up to little n of bk. Right, because absolute AK is less than or equal to bk as soon as little k is bigger than big N. But tell me, what is the, do we have an upper bound on what this, how big that pink sum can be? U.
let U be an upper bound on that sum. Since U is an upper bound on the sum, from k equals big N to little n of bk. Is that final thing just a constant? That whole last step? Have I just found an upper bound on the sequence of partial sums for Sn? Thus, Sn, thus the sum from k equals 1 to big N plus 1 of absolute ak plus big U is an upper bound on Sn, at least when little n is bigger than big N.
So I found an explicit upper bound on Sn as long as little n is big enough. Does that like automatically imply that Sn is just bounded above? If you like, on the one hand, it's increasing, so the smaller index terms will be less than the bigger index terms anyway. So this is a bounded sequence.
But ak is always positive, so Sn is increasing. Absolute value of ak is always positive by the monotone convergence test. Monotone convergence theorem, it follows that Sn is a convergent sequence, and so that infinite series converges. So it was like, there was this annoying subtlety that had like introduced this big N midway through the notation, or in the theorem, in fact. And the reason that I did that is because in the proof of the root test and ratio test, I'll need that freedom. Cool, so I'll stop now. Maybe the first thing we'll do next time is we'll, as a corollary, be able to show that this thing converges by comparing it to some other series. What series do you think you would want to compare this to?
1 over 2 to the
1 over 2 to the and if you like, that's something that you did in like Calc 2, right? In fact, you did things that were like way harder than that. Cool. So,
I am going to stop there.